talk about something that hopefully is of interest. And so this year they've asked me to go around with a talk about electromagnetics, both fundamentals and applications. So that's what we'd like to do today. There is, with respect to any site that we attend, then we've got, if this works, start.
Nobody apparently ever used the microphones.
Okay, that's okay. Well, technology. Anyway, I wanted to say we're really grateful to be here. I'm excited about being to Aarhus. The last time we were here was in about a year and a half ago for an IP workshop that was put on. And looking at the spectrum of people here, I think you're, just broad backgrounds and diverse, just diverse problems. I think, we have a lot to say. Before we actually go into that, I really do want to thank both Espen Auken and Anders Best, who's, without these people on the ground, this would definitely not happen. So there's, challenges sometimes with trying to present something like this and interact with SEG and local groups. And honestly, I can't thank either of you guys enough. So yes. Before we actually start, I wouldn't mind if we could just kind of go briefly through it, and people just tell me, like, okay, your name and what your interest is with respect to job and electromagnetics, and just kind of why you're here. You don't need to spend a lot of time, but just it would help me just to kind of figure out who the audience is. Maybe we start right at the back. No, yeah, okay. After this will be electromagnetics. Okay, go ahead.
Here from Science and Surveys, yeah, electromagnetics.
Mainly what?
Mainly science.
Okay.
Geologist, I use a lot of specialist guys and interpretations.
I can do that. I'm from the Department of Engineering. I'm working with signal processing and collaborate quite a lot with these guys.
Okay, good.
So we're from Aarhus Software. We work with software and innovation.
My name is Søren. I'm an electronic engineer. Actually, I work with the team and I'm currently finishing my PhD.
Good. My name is Frederick, and I'm a third year here, and I'm just here by interest.
My name is Adrian, and I'm a geophysicist who works with geophysical modeling of skies and depth too.
My name is Henriette, and I'm a graduate student here as well. And my name is Bennett. I'm a third year student as well.
And I'm Thomas.
I notice you guys kind of collect together, right? You got the master student in the back, and then there's third year.
I'm also a master student.
I'm a geophysicist working with mostly ground-based, ECIP, groundwater related, and other shallow stuff.
I'm with Guideline Geo, Swedish company marketing the water system. So that would be the temp systems, and I also work with those software products and these water and software.
Okay.
My name is Niels, and I'm retired. So.
So that means he knows everything. So all the hard questions you can ask Niels.
My name is Stine. I'm originally a theoretical chemist. I am now a software developer with Aarhus Geosoftware.
Okay.
Us, I'm also Aarhus Geosoftware programmer.
I'm also a programmer, but I'm at HTT. So that's a programming.
Ja, dann kan I also work for Aarhus software as a
Yeah. Also working with the software. Not as a programmer, but as consultant supporter in working with these guys.
and Dino, and I'm a PhD student at HTB here at the department and working with IP, but also some
Simon, I'm with Geophysics, and I work mainly with geoelectrics for downloads.
I'm Anna, and I'm working locally and using geoelectrics mainly for pre-construction surveys, so in mapping and horizontal fields.
Okay. And Maria, I'm also working at Code. In the past, I've been working a lot with farmer mapping, that's ERT, and SkySat, and also, say, just water temp, and yeah, now it's mostly for also infrastructure.
Yes, I'm Niklas. I work with SkySat Surveys. I work with research and development.
Thomas Stensen, and I'm also working at SkySat with handling data.
Now coming from the Geophysical lens, we're using the results of this you can get those big results that we use in our mapping.
Perfect.
Now from Mexico, working at the geophysical data acquisition.
And you're also working for Schlumberger, and I'm a seismic guy, so I'm interested to see what this is going to add to the picture we see with seismic there.
I'm Solveig. I'm also from SkySat Surveys, so I work with the acquisition of airborne electromagnetics.
My name is Bo Inversion. I'm from the Department of Agroecology at the university. I'm not a geophysician, but I'm interested in soil physics, hydrology, soil mapping, including mapping of tide rains.
I'm Barry. I'm with the U.S. Department of Agriculture, research scientist there. First on using geophysical methods for agricultural applications.
I'm Asbjørn, and I'm a second year student here.
Yeah, my name's Karen. I'm also from second year. I'm really interested. Oh.
Yeah, I'm Rasmus, and I'm a project manager at SkyTem.
My name is Sarah, and I'm a colleague of Rasmus at SkyTem, working with TEM and magnetic data.
I'm Jens. I'm a student working on my thesis about magnetic resonance sounding, and I'm just interested in electromagnetic methods in general.
Mm-hmm.
I'm working on mineral exploration with EM. From Greenland.
Okay.
And my name is Anders, and I am associate professor here, and I visited DOC as early as 2002 in Vancouver, and since then we've had sort of contact on and off. So it's really, really good to be here. I'm looking forward to the next couple of days.
2002? Wow, that's time goes. So you've told me a bit about yourself. Let me tell you a little bit about me. So I went to Scripps Institute of Oceanography, and my supervisor was Bob Parker, and also worked with Freeman Gilbert and George Backus. These three people, as far as I'm concerned, are kind of the grandfathers of the serious development of the geophysical inverse problem. Just to give you a bit of history about where we are, maybe I'll use this screen. This is a timeline. And if we look to see, okay, where were we, what was the state of the art in 1975? At that time, we could handle maybe 1D problems, DC, MT, maybe 50 variables. By 1985, maybe 2D, DC, resistivity IP, sort of 1,000 variables. 1995, now we can get into the first 3D problems. So that's the 3D gravity, magnetics, DCIP. 2005, with iterative solvers, we're able to solve the 3D frequency, that's the F, and time domain EM problems. And that meant that you could solve a problem with maybe a few sources. Two big things happened here. One is the ability to take large matrices, sparse matrices, and to factor them. So that allowed for direct solvers. And then also microprocessors, so that allowed you to have, to spread the computation along many different processors. That ultimately means that by about 2015, we could invert 3D frequency time domain EM with actually a lot of sources. And that brings us up to the disk. The point about this slide is that I think with the results in computational power and advances in inversion methodologies, we can now pretty much solve any EM geophysics problem for which we have data. So that's a big leap. There's another thing, too, that's actually been really important, and that is the development of instrumentation and data acquisition. Today, we can collect more higher quality data than could ever have been before. And we've got the whole SkyTem team here to kind of verify what that latest technology could be. And so it could be applied to large ground water studies and marine EM. We've got offshore stuff for hydrocarbons. Here's an example of magnetic tellurics. That's the map of Australia. Each of those is going to be a dot for a natural source and T station. So lots of data, high quality. Another major aspect has to do with the ability to have open source resources and making use of the web. It allows us to kind of collaborate, to share, to test changes, do some interactive computing. A lot of the things I'm going to be talking about have been developed through open source computing called SimPeg, and we'll talk more about that tomorrow. But you'll see lots of examples today. And lastly, we've got many applications. So electromagnetics can be used for minerals. Well, we had one person here. Yeah. Contaminants, most people are interested. Water issues, important. Geothermal energy. Unexploded ordnances in some countries, hydrocarbons, slope stability, geotechnical work. So these are all applications. So we seem to have the basic ingredients. We got application problems, we've got high quality data, we can invert those data sets, and we've got web tools to communicate. So seems like we're all set to go, but what's the roadblocks? Well, if you think about it, there's a lot of them. So in general, geoscientists, first of all, they don't realize the role that EM can possibly play in helping solve their problem. They don't understand the technique. The terminology is confusing, right? These EM guys are talking about, real data, imaginary data, what is that stuff? And the other thing is EM is complicated and it's not intuitive. There's things like seismic. You can see an acoustic wave going down, bouncing back off and coming back, and it's, you plot up the data and you've got an image of the geology. Can't do that with EM. The other important, or at least another important problem is, so you have a problem that you're trying to solve, whether it's a groundwater problem or mineral exploration or whatever. And then the question is, okay, what's the connection between my problem and the physical properties? Because ultimately that's what geophysics does. It tells you something about distribution of physical properties. But to make use of that, you have to relate it to your problem. So understanding that connection is A, non-trivial, but B, fundamental. And then once you do decide that you're going to use electromagnetics, then you got this whole host of things to do. Should I use DC resistivity? There's a lot of people here using ERT. Should I work in, if I work time varying, should I work in frequency? Should I work in time? Where's my surveys? Are they in the air, on the ground, downhole? And what do I expect for resolution? So there's one question about that. And lastly, I think there's kind of a comfort level in before you apply a technique to know that, okay, somebody else has applied this and it worked. So the question is, are there situations similar to mine in which EM has been applied? So those are the roadblocks. And the goal of the desk is really kind of try to get rid of them. So by the end of today, which is actually going to be a very long day since we now started at 9, so if people can stay till 6, that's going to work out really well. We're going to try to get rid of them. So that's my goal. By the end of the day, most of these things will now be much more transparent. So it seems that we've got a perfect storm here, and we can take advantage. And what have we got? We got problems. We've got high quality data. We've got the inversion capabilities. We've got web tools to communicate. Here's the disk. Why don't we put it all together and see where we are? So that's a good idea, but we're missing one important ingredient. What is it? The important ingredient?
The user?
Pardon me?
The user?
The user, even better than that. All those people sitting in the back row. People, the users were okay, right? But we need all those bright master's students, undergraduates, and even the professors. It's okay. It's never too late to have an idea. Right? I got 2 people here. One is Sagi Kang, who was here a year and a half ago at the IP workshop, and the other is Lindsay Hagee. Both are co-presenters in this discourse, and see a lot more of Lindsay tomorrow. But it's really, it's that next generation of people that have the brights and all the savvies that are really going to carry all this forward. So the goals for the disk, well, I'd like to inspire you. You see a variety of potential applications, and we're going to illustrate the effectiveness of EM through the use of case histories. Also want to build a foundation. It's important that you really understand the basics of EM. They're actually not so complicated, but there's so many people out there that try to apply EM, but they're just missing a little bit of the basics. And believe me, you can get screwed up pretty quickly and spend a lot of money basis. We're going to work with interactive apps. The group at UBC has been really exemplary in trying to develop tools that you can just use on the web, that you can ask questions and get some answers. And we have an open source resource given by here. The SEG actually requires, or they've always required, that whoever does the disk writes a book. Well, writing a book is a big deal. So it's a lot of work, but the other thing is that the moment that you write a book, it's out of date. That book goes to press, and it's got lots of things that are out of date. So we're going to have everything here open source on the web. You can read it, you can edit it, you can add whatever you like. We'll talk a lot about that. We want to set realistic expectations. Success and failure is all determined relative to the metric of what your initial expectations are. So we need to have them realistic. And the other thing, this is extremely important for us, is that we want to be a bit of a catalyst here for promoting the development of an electromagnetic community. We do that through open source software and capturing case histories worldwide. And we've actually got a number of case histories from Aarhus, from Denmark here, with respect to kind of high impact cases for the use of electromagnetics. So our resources at EM GeoSci, how many people recognize that particular suite? I got about half. That's good. So this is a book edited by Misak Nabigian on electromagnetic methods. And there's a wonderful chapter in there by Ward and Holman, Stanley Ward and Jerry Holman. And it's got all kinds of really fundamental information, talks through the equations, how to solve this, how to solve that. It's great. Every student of mine has gone through this. What we want to do is, is to take this book, however, and actually make it live. And that's what this website does. It's got lots of stuff in here with respect to backgrounds, but it also has case histories. Case histories are really important because they show how a particular technique can be used. We're going to parse our case histories down into a series of steps, 7 steps, which I think most people who do applied geophysics would kind of naturally think this is the way to go, but it really helps with the communication. By breaking it down like this, I can easily talk to somebody and find out, okay, where's their problem? Where are they in the scheme of things? And first is the setup, just trying to decide, okay, what is your problem? Next is what physical properties am I really interested in? What survey should I do? What data do I collect? What processing is done or inversion? What's my interpretation? And then last, some kind of a synthesis where you actually see, okay, how did I impact upon the problem? So that's a really logical way of breaking down any kind of a case history. And what we have on the website is kind of a précis version of a case history. Usually it's tied to a fundamental paper, like your work on Casted. And so that paper is available, but so too is this sort of easy to read, parsed down version. And that's how we're going to present the case histories today. The other thing is that you can edit all of this material on GitHub. And so everything is published out through Creative Commons licenses. Why apps? If I look at this equation, so this is Maxwell's equation. Okay, that's the equation, right? There's a lot of information in there, but you just look at this and it's like, well, okay, not really sure what's going on. However, you can take that equation and make it into an app. Okay, so this is actually a grounded dipole in a full space, and you're allowed to change different parameters as far as background physical properties or frequencies or whatever, and plot out a field. You can start to ask questions. And then you can start to get results and see, it just helps the learning process. So we've made a lot of effort into developing these apps. So how are we going to achieve our goals? Well, we're going to connect to relevant applications, select a particular type of survey, use the apps to explore and ask questions, and then we'll show the success in a case history. So that's going to be the procedure as we go through. The agenda for today is a lot. We're going to do something that I don't believe I've seen anybody else do. That's why it's actually going to be a pretty long day. But it's going to be a very interesting day. And by the end of the day, you will have seen a complete spectrum of electromagnetics. Because we're going to start off with a DC resistivity problem, which people here are very familiar with. We'll look at some EM fundamentals. And then we'll do inductive sources. So all the SkyTem people, here's where you are. Grounded sources, interestingly enough, doesn't seem to be used here. Plays a huge role in a number of different problems. So that may be something that people haven't really seen. Natural sources, magnetotellurics, ground penetrating radar. Now we're getting up in frequency. And IP, again, Aarhus is an area where there's been a lot of work that's been done on here, but we're going to do all of it. So that's it's an ambitious schedule, and I think, however, there's a wide variety of people and there's a wide variety of problems. That I'm hoping that there's going to be something throughout the day that's really useful for everybody. And if there are experts, we're not really targeting you, but I go for coffee with a group of people. We go every Saturday morning, 9:30 to 12, 2.5 hours. our coffee break. We've been doing this every Saturday morning with the same people telling the same jokes for 23 years. And the one thing that's kind of nice about this is that every morning that you go in, there's a different saying. And so there's somebody who has a quote. And this was by Doris Lessing. And here's what the quote is. That is what learning is. You suddenly understand something that you have understood all of your life, but in a new way. And I'm hoping that even for people who feel like, okay, they're kind of expert in this, maybe there's some little wrinkle in here that we can say that kind of enriches your understanding about that problem. So the DISC is a 2-day event. We have some challenges with the SEG. SEG wants this to be a 1-day event, just like it's always been. That's not enough time for us. We want to have a 2-day event. So the first is the DISC course today. So I'm going to hope that everybody can come to the second day, but if you can only come to today, then we're going to try to get through at least a first pass on those agenda items. Tomorrow is DISC Lab, sponsored by Jeff, and here we're going to do a number of things. We're going to carry over a few of the things that maybe we haven't been able to get today. And one of the most important things is that we want you to talk to us about the kinds of problems that you're working on so that we can capture what kinds of problems people are working on worldwide. So we've done this now worldwide. I guess this is about 18 presentation. We'll have about 30 altogether. And in each location on that second day, we've got anywhere from 5 to 15 people who give a 5-minute summary talk about, okay, here's my problem, and here's what I want to do. This is where I'm at, or this is my questions that I have, but just to kind of outline them. Those are captured, they're put up on the web, and they're there then for you or anybody else to see. You're shaking your head. You don't want yours on the web? You don't have to have it on the web. You have options. Some people don't. But most people do, and they're actually, what a wonderful resource this is. By the time we're finished, I mean, you could look, okay, what are the problems that people are working on in India or Malaysia or Australia? I mean, it just helps understand where EM is coming in, what the problems are, and helping to develop this community that I talked about. Let me share that. So if we can do that, it'll help connect everybody, and it will kind of increase the visibility of the field. So for you to connect and contribute, how many people have used Slack? Anybody? Well, we'll send you some information around about how to use it. It's a channel. You can communicate with anybody else in the group. You can share pictures. You can ask questions. So in fact, if you sign onto Slack and you could ask a question and Lindsay could vet it and even answer it, then I don't have to be embarrassed by not being able to answer it. It will actually work out very well. And then, yeah, so for contributing to EMGeosci, case histories, there's content. Every place you go, there's somebody who's been teaching something and got some way. Niels could probably add something here as far as the content, just how to think about things. And then there's software development, one that we've been working on at the same time. So that's kind of the goals. I now want to just kind of introduce a little bit about electromagnetics, and then our plan is that we'll introduce a bit of electromagnetics, and then we'll do a little bit of DC resistivity, and then have a later copy. So here's 3 problems. Here's a mineral exploration problem. We want to try to find minerals, maybe unexploded ordnance, and maybe water. Just kind of 3 random problems. So how do we locate and characterize that? Well, we've got to have physical properties. And the following 3 physical properties are all connected with electromagnetism. The first one is electrical resistivity. That's the ease with which, or quantifies the ease with which a rock can pass electrical current. And the resistivity is given in ohm meters, and noticeably it varies by many orders of magnitude. Very resistive rocks are 100,000 or maybe even 1,000,000 ohm meters, and very conductive rocks are just a small fraction. So massive sulfides are really conductive, igneous and metamorphic rocks are very resistive, and a lot of the stuff that we do kind of falls in the middle. A couple things about this is that even if you knew the resistivity of the rock, you certainly can't tell which rock unit it's in, and any particular rock unit has got a whole range of resistivities. The other term that I will use consistently throughout presentation is conductivity. It's just the reciprocal of resistivity. So something that's on the bottom scale here, we've got high conductivities over here. That's our massive sulfides. Really low conductivities are over here. So and EM people do this. They just kind of continuing flip between conductivity and resistivity. Just remember that one is the reciprocal of the other, and we try to make it so that we're talking in terms of units that have reasonable values. That's the first property. Welcome back. Yeah, 3 a.m. Arrival back in Aarhus. I'm surprised. I didn't expect to see you till noon. The second physical property is dielectric constant, or really the relative permittivity. This is going to become very important when we do the ground penetrating radar, but again, air has a relative permeability of 1, fresh water is 80, and everything else is kind of in between. And lastly, there's magnetic susceptibility, which can vary, again, over orders of magnitude. The big guy on the block is magnetite, and smaller ones are sediments and metasediments. So a large range of magnetic susceptibility. In general, the kind of cartoon representation of what is going on, we're trying to find some information out about these physical properties. So we need a source that puts energy in, and we get data out, some kind of a response that we can measure. So that's energy source in, there's properties, and we got some data. And everything we do today is going to be involved around these equations. This is not a mathematical heavy course. This is about the only system that we're going to see, but we're going to see it a couple of times, and we're going to kind of parse it out a little bit. I'm just going to tell you a little bit briefly about what's going on here. So this first one is called Faraday's law, and it says that a time-varying magnetic flux gives rise to an electric field. This is Ampere's law, says that current gives rise to a magnetic field. And then we have constitutive relationships. So here's one of them. It's Ohm's law. It says that a current is equal to the productivity of the electric field and the conductivity. So that's the relationship between current density and the electric field in a physical property. So let's just take, let's just kind of get a feeling for where we are and the flexibility that is going. So here's our cartoon. Here's our source. So what could we have for energy source? Well, you could have something that looks like this, so the SkyChem people would recognize this. So that's just a loop that is carrying a current. So that's called an inductive source. On the other hand, we could take 2 wire probes and attach a generator in here, and we've got a grounded source. So we're going to have inductive sources and grounded sources. The waveform for the current could be harmonic, just a sinusoid, or it could be some kind of a transient circuit. time domain system. And then our location of our transmitter could be in the air, as it is with SkyTem. This inductive source could be sitting right on the ground. And in fact, you could even put an inductive source in the borehole, and similar with these guys too. So you got lots of options. That's for the source. What about the data? Well, what can we measure? We could measure a magnetic field. We could measure it on the surface, or we could fly an instrument up there. To measure electric field, we need to have 2 probes. So they're done on the surface of the Earth to measure this electric field. So those are the guys that we're interested in here. By the way, I didn't mention in the previous slide, but we're going to use the capital letters here to denote what's happening in frequency domain when we've got harmonic signals. And we use lowercase when we've got sort of a transient. Okay, so we've got data. Which field do we want to measure? Do we want to measure an electric field? Do we want to measure a magnetic field? We've got options. And also, if it's a field, then it's got direction. So there could be multiple components. So we're going to have to contend with those things. And then which frequencies? Do we want a low frequency or a high frequency? Or if we're in time domain, which time channels do we want to work with? And finally, we've got just the whole aspect of location. Do these things want to be in the air, on the ground, in a borehole? So the point about this is that there's starting to be a lot of options here. You mix and match, combine sources and receivers to try to get out some information. So if we look back at our 3 problems that we just talked about, we actually see that electrical conductivity is diagnostic for all 3 of them, for the minerals, for the water, for the unexploded ordnance. So we're going to, today, almost always, be concerned with electrical conductivity, or its resistivity. So what I'd like to do now is let's revert to the first electrical problem, which is DC resistivity. So how many people have been involved in an ERT or DC resistivity survey or have worked with the data? Yeah, about half. That's good. DC resistivity. So we've got a source, interact with the resistivity. So we're going to work mostly with, I'll try to be consistent, talk mostly about resistivity. And we're going to measure some data. What's our motivation for this? Well, minerals, although it's not a big one here. In mine geophysics, trying to find water, oil and gas, groundwater issues, or geotechnical issues. All of these could benefit potentially from the use of a DC resistivity experiment. Electrical conductivity is actually, we saw this diagram before, but the point that I want to make here is that the resistivity or conductivity of the rock actually depends on a lot of things. So here is a small scale image of a piece of rock, and that's a penny or a 1-cent coin. And you can see a lot of things happening here. You got kind of different, almost different kind of rock type on here versus here. There's issues. One looks more porous. It's got more holes in than the other. Probably the way in which those pores are connected is different. And then what fluids you put in would make a difference. And then, you know, the metallic content of the solid matrix. So it's complicated. There's a lot of stuff going on, and that probably tells you why, if you have a particular rock type, there could be quite a bit of variation in that electrical resistivity. So we're going to kind of step through the DC resistivity. I'm going to start at the absolute beginning here. But it's important to do that because the things that we'll work with, especially the whole concept of charge buildup in a DC resistivity experiment, is actually going to play a really big role when we do electromagnetics. And then we're going to have a case history for a mineral deposit and yeah, talk about the effects of the background. So here's the basic experiment. So what we're looking at here is kind of a cartoon model of the Earth. It's, you can think of it as a mineral deposit where we've got a highly conducting region inside, very low resistivity. We've got a blue region in here, which is very high resistivity. There's some overburden, and it's all in the background. So our setup is that we're going to put, first of all, transmitter. So we're going to take a generator or battery, hook it up to two probes. So that's going to be these blue guys here. And we're going to measure the potentials out here. So we're going to, first of all, put in these current electrodes. And now we get currents, and they're going to flow in through the Earth, and they're going to be distorted by whatever resistivity structure we have. An important thing is that as those currents are flowing through, there's actually going to be charge buildups on any surface that has got a change in electrical resistivity. And those potentials that are obtained from these charges can be measured up here with a voltmeter that's attached to two probes. So that's the basic experiment. And what I'd like to do now is to just kind of go through that and sort of see, okay, how do we actually get the resistivity of the rock? So let's go back to Maxwell's equations. In a DC resistivity, DC stands for direct current, so we're zero frequency, so nothing is changing in time. That means that this first equation here can be written like this, which says that the electric field is the gradient of some potential. Ampere's law gets written like this, Ohm's law is like this, and we put it all together. This is probably one of the most classic equations in, well, perhaps all of the geosciences, because this is your groundwater kind of problem, this is your magnetics problem, this is your DC resistivity problem, where you've got divergence of a physical property, sigma, grad potential is equal to source. So if you can only ever understand one equation, you can only solve one equation in your life, that's probably a good guy. It's sometimes called the mother of all equations when you talk about partial differentials. So let's just see what we got. So we take, let's suppose we have a homogeneous Earth, and we're going to stick a current into that. Then there is an analytic relationship here that's says that the voltage is given by this expression. So the resistivity, the current, and R is your distance that you're away from the current. Okay, so let's look at some pictures of currents. We're going to see a lot of pictures of currents because if you understand where the currents are flowing, then you really understand a lot about what is going on and what you want to measure. Let me put a single current in the ground. Looks like this, and as you'd expect, just because of symmetry, it's going out uniformly in all different directions. And our relationship between the voltage and the resistivity is given by this. So the voltage or the potential that we've got is actually infinite right at that current electrode and falls off as 1 over R. So interesting. Well, and in a way, this is kind of amazing. If you take this very, very simple equation, you just you just rearrange it. So to put resistivity on this side, and this, you actually have an expression that allows you to recover the resistivity knowing R, B, and I. So it doesn't matter what point you go out here, you measure a potential, plug it back in, and you get a resistivity. In this case, you get a resistivity of 500 ohm meters. So if you think about it, that's kind of interesting, isn't it? You put a current in the ground, and you're just trying to find this resistivity, right? And it doesn't matter where you go, you just measure a single number, and that allows you to recover what the resistivity is. In reality, we can't do that, of course, because our survey system has to have 2 probes for the generator, has to have 2 probes for the potential. So we end up with a system that looks like this. It's a standard 4-probe system. We're going to be consistent throughout the day that A is going to be the positive current electrode, B is the negative. And so what happens here? Now if you look at the current, here's the positive current, and you can see how things are moving out like this. But they're going to be drawn into the negative. So our current paths now look like this. So that's different than they were. The electric potential now looks like this. So it's got an infinite positive and then an infinite negative. All of the geometry, the distances between a current and a potential electrode are known, and we can put them into a formula, and we could write that the potential difference that we see between an AM and an N electrode here is actually given by this formula here, which this guy is just a geometric factor, and we could rework this to give you a resistivity that looks like this. So we're kind of at that same thing. If I go back here and now I take a voltmeter, put it any place on the surface of the Earth, measure the potential difference here, I can actually put that into this form and recover the resistivity. And if I do that here, I get 500 ohm meters. Okay? So that's our way of going from a measurement to actually what the resistivity is. So what's going to happen if I change this and make it a little bit more complex? Let's suppose I put, instead of 500 ohm meters, I put a less resistive layer, 100 ohm meters at the top. What do you think is going to happen to these currents? Anybody? Simon?
Current's going further eastward.
The currents will, yeah, they're going to tend to flow through the conductor. They're actually going to flow like this. Now you see more currents are concentrated here. If I do a measurement of the electric potential up here, plug it into the formula, I actually get a resistivity of 226. So it's not 100, which is the near surface, and it's not 500, which is the background. It's some kind of an average over there. So that's why we sometimes subscript this with A. So now this is an apparent resistivity. Okay, and it's 226. So we got some apps that allow you to play with this. And these are great because now you can start to learn a little bit through varying different parameters of the resistivity of the layer and thickness of the layer and where you're putting your electrodes. And as I say, these are open source, you're free to use, and all contributions are welcome. There's two things with respect to trying to find the distribution of resistivity. There's soundings and there's profiling. We're going to talk about soundings first and the different ways that you might use it. So the geometries, when people talk about geometry of a DC system, they're just talking about, okay, what's the what's the configuration in which the currents and potentials are measured. And this is one called Wenner array, so it's kind of equidistant here between all of these. And then there's Schlumberger. It's kind of a kissing cousin. There's really not very much that's different significantly, but generally this is a little bit, this is fairly short in here compared to that. In a sounding array, what we're going to do is kind of pick a geometry, and then we're just going to make it farther, expand the geometry. And we're going to end up with what's called a sounding curve that looks like this. So it's going to be an apparent resistivity on this axis versus something that is related to the size of the array on that axis. And the intuition is again built up through through images of the currents. So I'm sure your name was. Yep, Sarah. Sarah? Yeah. Okay. So if it's okay, I'm glad you said it. Okay, so if let's suppose I'm trying to get some information about Sarah, and we're assuming that everything is just going to be 1D here. But if I take my current electrodes and I put them in like this, right? So I got that distance between them. Then the currents just kind of go like this, and there's nothing getting back there, right? So that's what's happening here. I've got current electrodes that are really close together, and most of the currents are in here. I calculate my apparent resistivity. I see it's kind of like 100 ohm meters, which is basically this. However, if I expand them a little bit, so maybe now they're big enough, so there's currents actually going to Sarah, and she started to affect things, and now we've got 135 ohm meters, and there's my sounding curve. And if I make it bigger, get something that looks like this. So the point about this is that the kind of depth of penetration is somehow connected with the sort of the size of this array, and we could get a sounding curve maybe that looks like this. So in summary, that's what we'd have for this. We had 100 over 500 and really short spacings. Basically, we're seeing this. Even at really long spacings, and this actually turns out to be important, you have to have a very, very big array before you actually, affected, so that you're not really affected by that upper level. Well, and we'll see this too. We always have to have big arrays to look.
Is there a rule of thumb? Sort of how far to see how far down?
Yeah, factors of 3, often, but that's a pretty coarse rule of thumb. But actually, a factor of 3 is pretty good.
For seismic, it's about 4. So yeah.
There's right. So here's an apparent resistivity curve. That is data. That's what it is. This is data up here. And this is just some kind of scale length of the size. That does not tell you the geology. You can't look at this curve and get what geology is. So in order to do that, we need to invert the data. I've spent almost my whole life doing inversions and trying to work with my group and invert all these different kinds of data. We're not going to talk about inversions. That is just a whole subject in itself. I'm just going to tell you basically how we're going to solve this problem and how we're going to solve every other problem that we do. And the idea is basically as follows. We get some data. Could be all different kinds, complicated data. And the inversion process is one in which we divide the Earth up into cells. In a 1D case, those could be just layers. In a 2D case, those are infinite prisms. And in a 3D case, they're just cuboids. Okay? So we divide the Earth up into a whole bunch of cells. And then the inversion algorithm adjusts the values of those cells so that we fit the data. And we also have other a priori information that we would like to incorporate in So we're just going to assume that's done. And if we do that, then we might get out a representation, especially if we're looking at a smooth model, maybe a curve that looks like this. So the true model was this step function, but this is now actual depth, and that is true resistivity. Okay, so that's the procedure. We want to ultimately get to that. So let's go back to where we were, and I want to kind of come back to this concept of charge. So we've got a positive current going through like this, and it's steady state, and that means excuse me, that means that the current density, at least flowing normal to this, that the current density is constant through here. Okay, so nothing's changed in time. Current density is constant. So that means that the current density J1 on this side has to be equal to that on that side. Okay, but J is connected through Ohm's law. That J is just sigma E. So that means that sigma on this side, product of sigma E, has got to be the same as the product of sigma E on this side, but we already know that the sigmas are different. So that must mean the electric field is different. And now the question is, okay, how can the electric field be discontinuous? How is it that I can go across a body here and have a discontinuous electric field? Where does that come from? Well, if you rewind yourself back to your first year physics course, we remember that on a boundary, if we take a plate, we put a charge on that plate, that the electric field goes outwards from the positive charge, so it goes this way, this way. And that means that if I'm coming across here, I'm going to see a discontinuity in that electric field. Okay? So that's what's happened. So the only way I can get a discontinuity in the electric field is I have to have a charge. So that's really important. And we're going to see this throughout the whole day. We're going to drive currents through bodies, and those currents are going to cause charge buildups. Those charge buildups give rise to a potential through Coulomb's law. Okay, important. So let's just look at these. Let's just look at some charges and potentials. So here's what we're now going to do is put in a cylinder. So it's going to be a conductive cylinder in the background here. And first of all, you can kind of guess what's going to happen, and Simon basically alluded to it. You have a conductor here, current's going to take the least resistance path, and it's going to, you can see how he's kind of getting sucked in here and then coming out. If we looked at so that's the total currents. Most of the time we're kind of interested in the secondary current. So that's the difference between this thing with the body and without. And if we look at that, here's the secondary current. So these are kind of interesting, right? They're almost kind of like a little dipole. What's actually causing those guys? It's caused because of this charge buildup on the outside of this cylinder. So as the currents come in, you're going from a resistive to a conductive, you get negative charge buildup here. As they come out, you get positive charge. And then those charges give rise to a secondary potential, and that's the measurement that we're really trying to capture. Just to get some idea about what's going on here, let's just look at a DC resistivity experiment. This is going to be kind of a gradient array, so we're going to fix the A and the B electrode, and we're just going to kind of move this guy around. When we do this, and we're sitting right here, then we get a reduced electric potential. And if we plot that into our formula for apparent resistivity, we get 430 ohm meters. So that's okay, right? Because the background was 500, and now there's more of a conductor in here. So we're kind of going down. So the apparent resistivity is at least taking a drop. We get 430 ohm meters. If we do it up here, however, put that measuring potential up here, we get something that's very surprising. This number is 502. Doesn't sound like much, but it's more than any resistivity that we have, because the background was 500, and that was much more conductive. So the question is, why? How is it possible that we could get an overshoot in that? What's going on there? So you can think about that. We're going to come back to that. Why could we get an apparent resistivity that's actually larger than any resistivity that's in that subsurface? So this is kind of what we have in composite. If I now go to, so that was a sounding in which we just kind of progressively look deeper. Now I want to do profiling. Okay. So let's suppose now that I've got an array, and the only things are really small. So I'm coming along here, and I don't see anything beyond here, except if I got to Lindsay, then I'd see something. She's sitting right up the top. Okay, so it would be kind of like this here. So I've got an A and B electrode here, an M and N. I'm just sort of moving those guys along, and my depth that I'm seeing is really small. So basically, I'm just seeing this 500 ohm meter half space. If, however, I make it bigger, okay, then now I'm actually sensing Zara, and as we go along, that is altering my measurement, and then I'm going to get something that's. So the upshot of this is that for very short spacings, very small arrays, I just send something up here. For larger arrays, I get something that looks like that. So now I'm really starting to get a low resistivity. Notice the overshoots here are actually pretty big. So it's 530. So that's basically the idea. We've got, if I've got a 1D Earth, then I can just do a sounding, no problem. If I've got a 2D Earth, I want to do both things. I want to do kind of a profiling to see the differences, but I also need to make my array larger. So I'm going to translate. People talk about a whole host of different setups as far as geometry. So Wenner geometry we've already talked about. Gradient is generally you put out a wire and you just take data in between. Gradient. We'll be talking about pole, dipole, dipole, dipole. Every measurement actually has 4 poles, but sometimes you could take one wire. For instance, if I took a current wire and I just ran it a couple of kilometers out that way, then it's so far away it's kind of like infinity, and then you say, oh, that's a pole dipole. And you could do that with both of these guys, maybe have a pole pole. How many people have seen a pseudosection? Actually, I should have asked, how many people have not seen a pseudosection? It's more interesting. Okay. So you have to plot the data up someplace, and if you have a 2-dimensional geometry, then what we're going to do is do the following way of a presentation. So we've got a dipole-dipole array, and to plot it at some point, we're just going to take 2 45-degree angles and we plot it at this point. If we then move this farther away, we have something now that looks like this, and oops, farther away looks like that. So the idea is this is a plotting plane. Again, it's just a vertical axis that is somehow reflecting increased depth, but is not it's not a real depth. And what we're plotting are the apparent resistivities, which were not true resistivities. But if I build this up, so what I'm going to do is make a pseudosection. I'm going to take this guy here, so the currents here, and then I'm just going to move this out here. That's going to plot this line. And come over here, do the same. Da, da, da. So we're just gradually building up the plot of points, and we can contour it, and we get it like that. So that's a pseudosection. It's a picture of the data. I mean, there's some interesting information. So that's low resistivity, it was high. That is not the geology. I just want to show you a couple of examples. So here's a situation. You've got a uniform background, and there's a conductive block here. If I go do a DC experiment over that, I get an apparent resistivity that kind of looks like this. So this is sorted depth, and this is horizontal location. And you get a picture out that looks like that. People that were familiar with this would recognize, like, oh, there's probably something right here. I should drill here, right? I got to find something. Okay, you might have been lucky. Here's a case where it's a bit more realistic, and that is that we still have this conductive block, but we've got a whole bunch of little stuff of geologic noise. So these are little clays, whatever. And now we look at the pseudosection, and it's completely garbled, right? You can't make any geologic sense out of that. And another case that we've got is this one here, variable overburden, the topography. There's two conductive blocks in here. The apparent resistivity section looks like that, which is actually kind of clean, right? And it looks like there's just this one big target here. So there's a temptation to just like drill right on here, in which case you would have drilled right through here. Okay, so big take-home point, pseudosections, way of plotting data, do not make an interpretation from them. So that means now we have to invert the data, and we're going to do the same thing. We get our data, and put it into the inversion, and get out something that's hopefully geologic. If you do our buried prism, so this was the pseudosection that got me inverted, and we get something that looks like that. So that's kind of nice. Centrally, it's kind of located about where the center of the block is. It's smooth rather than blocky, but that's because of the inversion algorithm. We could have made something that was a bit more blocky, but we just choose to find a smooth representation. So there's a lot of information that is obtained from here. If we come back to this guy that was really garbled, this is interesting because you now see the block, okay, so there's your conductor, but you actually have recovered a lot of this nearer surface stuff. So you're that near surface structure, and maybe actually that's interesting to you for some reason. And if we come back to this GIF model, here was our pseudosection inverted. We get this. So we got lateral variability, two conductors, good to go. That was 2D. The world is 3D. So, might have stuff that looks like this, might have ore body like this, lots of topography, underground water. It's very variable. So that means our target could change in size, shape, depth. Background might be variable. And so now you're left with some really kind of serious questions. Okay, I can put currents in, but where should I put the currents, right? And then what do I want to do for acquisition? Do I want to just collect data along the line, or do I want to make it 3D? And which measurements do I want? Electric fields this way or that way? What's the effects of topography? These are all survey design questions, and they really come back to the crucial element of sensitivity. So if I were to ask you, within the context of geophysical problems, what you mean by sensitivity, what would somebody say? So you in Sorry. Yeah. Oh, sensitivity? That's not bad. Influencing data. Anybody else? So your name is? Anna. Right. Okay. Sarah, Anna.
Solvay.
Solvay. All right. I can probably do better that than I did with presenting a case history in Austria where they had all these geologic units. No way.
Like variations in your parameter, how much they will reflect in your system.
Perfect. So sensitivity is usually, so supposing we're trying to find this guy here, right? And then usually what we mean by sensitivity is that, okay, if I change a parameter here, it might be the resistivity of this, or it might be a boundary here, or what is the change in the data? And that's how we kind of quantify it. The thing is that we want to collect data that are sensitive to the target. And often what people generally do is just kind of throw everything into a hopper and say, oh, here's my sensitivity function. But I find that really complicated. And I think it's much easier to break this whole concept down into two parts. The first is just, okay, we need to excite the target. That's the first issue. And then once we've excited the target, then we somehow have to figure out, okay, where's the currents, and we want to somehow be close to it. But you find when you think about survey design and sensitivity that breaking these things up into two parts is very beneficial. So let's do that. Let's come back to our problem here. So here's our total currents that are coming in through here, secondary currents. Here's our charges. So we are exciting this target, right? There's no question. We've got lots of positive charges, lots of negative charges. This guy's excited. Okay, so that means that this location of the current electrodes is actually perfect. What about the measurements? Well, intuitively, you kind of already know what you'd like to do. You're measuring the electric potential, so you simply want to have at least one electrode that's as close as possible here. But if you're confined on the surface, then you're probably going to be pretty happy to collecting data that are just kind of collinear. So that's that's kind of the essence of what's going on here. And yeah, actually, if you, well, we'll go back to that. Okay, so we've excited the target, and because we understand where the potentials are coming from, all the charges, we could make some sense about where we want to measure, and maybe even which directions we'd like to measure. An issue that we haven't talked about is coupling. Okay, so I mean, I've got this cylinder in the first go around. Let's suppose I put a plate. Okay, so I've got a plate. I could have different orientations of a plate, right? So, excuse me. So here's my conductive plate. I put it in. We look at the currents. You can see they're distorted a bit, mostly at the top and at the bottom, and that they're going through. So you're doing something. But look at the change here. If I put the plate this way, now look to see how much the currents are changing. So coupling here, the orientation of my plate, my object with respect to the current lines is going to be very important. The other thing that we haven't talked about is conductive and resistive targets. I mean, should it matter? So in this case here, okay, I've got a conductive target. If I had a resistive target, do you think if I have a resistive target, what's going to happen to those, to the currents? Currents are going to kind of go around, right? So that's going to, currents are changing. means my charges must be changing. So let's look at this. So here's that conductive target. And if I plot out what the charge is, you know, you get something. So you're sensitive to it. You're seeing it. But look what happens when I have a resistive target. Now it's got to kind of go around. And now I've got all these larger charges. So from a point of view of sensitivity, we're going to have an easier time trying to find this resistive target than the conductive for this particular geometry. Okay, so these are things to be important. Okay, we're going to put down some current electrodes. The coupling is going to be important. Whatever I have as an object, you know, how it's rotated or how it's configured with respect to that primary field, that's important. But also whether the target is conductive or resistive. So that's kind of a summary about sensitivity. So you know, we need to drive currents in through there so that we get good, make sure that we've got good coupling. And then if we got enough charges built up, then we can design whatever receiver that we want and measure the potential. So now let's come back to our questions of survey design. Excuse me. I think we need, what is it? Would you have grappa? Maybe that's what we need here. The Danish drink schnapps, do they? Okay, so we're going to do survey design. What's our question? What's the objective? Okay. So if we have a 1D Earth, we want to, you know, have a 1D Earth interpretation, we're going to do a sounding. If we've got a target body that's 2D, that's no problem either. We do a profile and a sounding. And we're going to do it perpendicular to the geology. If we have a target body that's in 3D, now things are more complicated. We're actually going to have to go ahead and do, you know, some kind of a sensitivity analysis. And we're also going to be concerned about the background. It would be nice if there was just simple explanations that one could provide to say, oh, well, you know, here's an engineering book. I've got this problem. You do this. Life is not that simple. In general, if we've got a survey design, we would have to kind of come back to numerical modeling and just see, you know, what we're up against. So here's a 3D geology, and maybe there's some buried bodies, maybe it's a mineral deposit or whatever. And you want to see if your survey is sensitive to that. And the steps are really straightforward and, yeah, really well defined. So first of all, you need to have a geologic model. And then we're going to, so that might be this, assign physical properties, select your survey, and then you simulate with the target and without. So without the target might be the blue line, with the target is this red. And you can see, okay, there's a difference here. And then the question is, how big is that difference? So there's two things here. One is that, is it larger than an absolute floor value? So what your background noise is. And also from a percentage viewpoint. So for a lot of experiments, in fact, you probably do this for your DC resistivity, that if you're assigning noise prior to inversion, you'll have a floor plus a percentage. And the percentage is actually useful when you've got large dynamic ranges in the data. That would be true also with the SkyCam data. You're looking at different time channels. And you know, in order to be sensitive, then you need to kind of have this delta be larger than these guys here. What I'd like to do now is to kind of give them a bit of background. I want to go to case history. It's a mineral case history, but I think you'll find it very interesting. And actually, I'm particularly fond of this one because I believe this was the first 3D inversion of both DC resistivity and IP data that was taken for a mineral exploration project. We did this way back in, before 2000, about 1997 or 1998. And at that point, we were just getting to the point where we could try to solve those problems. The prospect is, it's called Mount Isa. So it's in Australia. So it's up in this particular region here. And we're going to parse this out in the 7 steps that I told you before. So the first is the setup. What's the problem? Well, it's a mineralized zone. It's called the Mount Novot Horizon. And it's sitting up in, it doesn't matter what these rocks are. They're different colors. They're different rock units. It's fine. But there's some volcanics and there's some siltstones and various things. And what we're asking the question is that can a conductive unit, which would be a potential target within these siltstones, can that be identified with DC resistivity data? So the first thing we're going to look at is the properties. So here's our geologic model. As I said, there's a number of rock units. The most important thing is this table here. We see that this Mount Novot Horizon, which is a mineralized zone, has got a high conductivity. Okay, that's good. But in order for anything to be visible, it has to be distinct from any of its background neighbors. So there's these volcanics in here. They're low conductivity. There's some siltstones that are moderate conductivity. So certainly this distinguishes itself from that. There is another kid in the block. It's called a breakaway shale or a black shale. And that's actually a very high conductivity. So the thing that we're actually looking for is a high conductivity, but not maybe the absolute highest. So we're going to collect data. It's primarily a 2D geology to first order. There's a predominant strike length in here. So the data that were acquired are DC resistivity data along these horizontal lines. There's 10 of them. And for each of them, there is a pseudo-section, right? So now we've talked about pseudo-sections. So this is a pole dipole. So the current source is here, and they've run the other current line way out in Hecagon. And then they successively measure the potentials as you go along here and then plot that up. And then you gradually move this current over and you just build up this pseudo-section. So what we have here are 10 pseudo-sections. The red means conductive. And you can see that there's some red parts in here. So those are, there's something that's pretty conductive. Okay? But those are data. They're not going to tell you what the geology is. The other thing I talked about was exciting the targets. So this is always putting the current in from like the left-hand side. If we wanted to excite the target in a different way, we might actually put the current on here and we get a dipole-pole experiment, which is what this is. So here's another 10 pseudo-sections. Very different, right? Look at the large reds that are in here. But still, they're pseudo-sections. So what we'd like to do is now we've got 20 pictures of data, and we really want to go ahead and invert them. So that's what this is. What we're going to see, so first of all, what's been done here is to take the Earth, model it as a cube, so now it's a 3D cube, invert the data, which means that we're going to have a value of conductivity for each little cell in there. And then that's what this is. We're then going to look at this in various slices as we go in and back, and then from top to bottom. And then it's going to rotate around. It's going to constantly change the isosurface level so that in the end you only see that part that's most conductive. So you can see that red part, large red. Now it's rotating around. And as I say, the isosurface level keeps changing here. So that in the end, you're seeing only the most conductive part. Okay. So this is great. So now we've converted data to geology, which is what we want. We had 20 snapshots of data, converted that. We've got a couple of things here. One is this great big conductor in here. Remember I talked to you about that black shale unit that was going through, and we got maybe a bit of a moderate conductor in here. This is what actually it looks like in color. The really good thing about here is that you've first of all gone from your geophysical data to a 3D inverted model that's got some information about geology. If we now try to look at a synthesis of what we've got, there's a few things that are going on. So first of all, there's this big conductor. That turns out to be a black shale unit. It's the big geologic kid on the block, but it's not interesting from a mineralogical perspective. The other, and you're barely seeing it at this point, is that we've got a moderate-sized conductor coming in here that is actually going to be this Mount Novot horizon. Excuse me. The point about this is that it turns out that electrical conductivity is not quite the total story here. What is really important is that this unit is also chargeable. There's an induced polarization effect that is really going to distinguish this. We're going to come back to the same example later on and be the last thing that we do. And we'll show you that that combination of DC and IP is enough to contend with that. But even at this point, we can see that we've actually done a pretty good job of unraveling things from the geology. Okay, so we're going to come back to that. There is a case history that I am not going to show. We can do that tomorrow. This is about monitoring an embankment dam in France, and basically it's using self-potentials. So this is where you get water flowing through a bank. Let's see, where's the guy here? Okay, this is basically what happens. So here's a river, here's a dam, and then you get water that flows through here. It creates a self-potential, it's called streaming potential. And basically the end result is that there's electrical charges that are built up on this end and on this end. And we could go ahead and we could measure, do a potential field measurement using DC resistivity equipment and measure what those potentials are, and then ultimately go ahead and try to find out something about the how the water is actually flowing in through that dam. That's a whole other story. What I want to do here before we break for coffee is look at the effects of the background conductivity. So this is actually an important part of any DC resistivity experiment, and also it kind of leads us into why we want to do electromagnetics. So remember what I told you about before? We've got 500 ohm meter background, then it's got this conductive structure in here, and the currents kind of get sucked in. Okay, suppose suppose that I put on a thin resistor. That's what we're going to do. We're going to put on a resistor. It's going to be very resistant, but we put something on just up here above the sphere. So what's that going to do to the problem? Who are? Anders. Anders? That's probably a good guess, isn't it? Yeah, I call everybody Anders. How can you? To
Well, I guess it's going to reduce the amount of current that will cross that layer, and what it will do to the model. So
no, that's good. I mean, we're interested first of all in exciting the body, right? So all we care about is currents. So if we put in a resistive layer in here, so that resistive layer actually goes from here to here, right? But all the currents stay above, and you can see, okay, they're going down here and up here, and I'm kind of shielded here. And if I computed my apparent resistivity, it's actually 1650. So remember, I was looking for something that had a low resistivity. Without the resistive layer, it was 430. With the resistive layer, it's 1652. Now, to show that it's just the resistivity layer that you're effectively seeing, here's an example now without that buried cylinder, and we still have the same apparent resistivity. So this is a really important point here. We have DC resistivity, looks fine, looks great, but then now you put in, a big resistor in here, and you're shielding the object that you're looking for. So you kind of hooped. Okay, what's going to happen if we take that resistor and make it a conductor? Person behind, yeah, you're good.
Well, it's still shielding it because the current's staying in the conductor without traveling much flow.
Right. So if I put a conductor in, then now the currents don't flow up here. They actually go into the conductor along here and up there. So I'm still shielded. My apparent resistivity is low. It's 47 millimeters, but that is purely because I'm just seeing. Okay. So that's kind of an interlude to. First of all, it does two things. It's a background to the DC resistivity, which it's just going to come in again and again through the day, especially the whole concept of charge build up. But the other is this effect of background, your background model. In the case of a resistor or hoop, in the case of a conductor or hoop, what we're going to do is come back, we're going to look at EM fundamentals, and then we're going to see under what circumstances we could actually see through that guy and find that buried target. So with that, let's have a break.
Do you want to try opening up the mic?
Oh, I think it's still a residual from the Vikrams. Remember yesterday, like how tight it was, and it just never. It might ease.
No. Do you want to try it? I mean, we can try setting this up. Just over the break and see if it works, and if not, then.
Yeah, maybe.
Because all we have to do is put it in your computer, and if it works, it works.
Okay, let's do that.
There was a request with
They are. They're already uploaded.
maybe I didn't look at them, but they are.
Yeah. So for those people that were wondering about whether the slides are available, yeah, so they have been uploaded, and also the whole performance is videotaped, so it's all on YouTube. So, and also you can look at other places that we've been. They're both the slides and the presentations are there also. And there's also a blog that you can look at to find out what's happened. Unfortunately, the picture that was just on, I'm not sure how many people saw it, was a picture from Adelaide, where the hosts there took us out for this. Probably one of the best Thai food restaurants and dinners that we had.
No pressure.
No pressure, but it was a really good dinner. Right? It's just like, whatever. Good, okay. We want to start looking at EM. And the reasons for this are really multifold, perhaps not perhaps very familiar to people here who are just involved in SkyTem types of stuff and inductive sources. But suppose that you've got large regions to be done. Let's suppose 100 kilometers on the side. I mean, that's difficult for DC resistivity. We saw that a resistive layer can shield a target. Sometimes currents are just hard to inject, or you've got rugged terrain. So a lot of reasons for finding something that's different than DC. So what we're going to do is kind of, again, go back to the beginning, the absolute beginning, because there's always, even if you kind of know all that, there's always little stuff that comes out that that actually turns out to be helpful. So here's our basic EM experiment. We've got a transmitter, receiver. They're in the bird. Here's a transmitter. Here's a receiver. And we've got a transmitter. It produces a primary field. Looks like this, kind of like a magnetic dipole. And then if those magnetic fields are time varying, it's going to generate electric fields everywhere. And if you happen to have a conductor, that's going to induce or generate currents. And the currents that are induced are also going to produce the magnetic field that could be measured by the receiver. So that's basically it. But I want to parse that out a bit. And I also want to do something that's perhaps a little bit different than, at least when I learned electromagnetics. The very first thing we did is do things in the frequency domain, because you can take a Fourier transform, and the equations are simpler. So we did all that stuff, and then you're like, oh, time domain, right? And it almost seemed like a different, like something that was really quite different. But what I'm going to do is put them together so that by the end of the day, you're going to have like frequency time, doesn't make any difference, and that the intuition will actually come from the time domain as opposed to working in the frequency domain. But you'll be able to see that they're really the same thing. So let's first look at the transmitter. So we could have a transient waveform that looks like that, or we could have something that's sinusoidal. The transmitter gives rise to a primary field that looks like that. And our equations, now these are going to be what are called quasi-static equations. They're almost the full Maxwell's equations, except there's going to be one term here, the time rate of change of the electric displacement, that we're going to ignore. This guy here is the one that we're going to bring back when we do GPR. But for now, we can ignore him, and we're going to be good to go. So let's first of all look at Ampere's law. Ampere's law says that J is related to the curl of H. Now, if you, for everybody who's really had a wire, okay, with a current going through, you know that you can get the direction of the magnetic field by using the right-hand rule. You put your thumb in the direction of the current, and there's a circular magnetic field that comes around here. And that's the relationship for the magnetic flux, falls off as well. The fact that we've got a curl here means that, so we have a current, and then it gives rise to a curl of H. So it means it's kind of circularly symmetric. So that's what that curl operator does, and you can ground yourself in this in the right hand. If we take that loop of wire and we roll it in on it in itself, so that we've got a current loop like that, now we have a magnetic field that is given by this expression. And there's two important things about this. One is the strength of this magnetic field depends upon what's called the moment, the magnetic moment, which is the product of the current times the area of the loop. So from the point of view of inductive sources, that is a really important point. And people are trying to constantly make bigger moment systems. The other thing that's important is that the magnetic field from here falls off as 1 over r cubed. So there's just a geometric decay. Faraday's law says, oh, if I have a time-varying magnetic field, that's actually going to give rise to an electric field. But remember, there's that curl operator. So time-varying flux, okay, gives rise to a circular electric field. There's also a minus sign in here, which is due to Lenz's law, or Lenz, and that helps define which way those induced currents are going to go. And we've got Ohm's law that J is equal to sigma E. So just to illustrate Faraday's law, we're going to use a simple circuit. Here we've got a magnet, so it's going to produce a magnetic field like a dipole, the same as a current loop. And at this situation here, everything is static. So we've got a magnet, we've got a coil of wire that's hooked up to a voltmeter. There's a lamp in the circuit. So if there's ever a current that's going to go through here, the light's going to go on, and it's going to go around like this. So in steady state, when we've got a magnet that's sitting out here, there's magnetic lines of flux that are coming through, but nothing is changing in time. The quantity that's really important is this something called the magnetic flux, which is the integral over an area of a plane with b times dot into n. So it's the normal component of B integrated across the surface of a coil. So that gives us the magnetic flux, but any current that's induced, or the voltage that's induced, is really related to the time variation of that magnetic flux. And then there's a minus sign. So you can think about it sort of being a bit of a circuit then that looks like this, with a voltage that's going to be induced. So at this stage here, the magnetic flux is constantly happening. If I push the magnet in towards, now I've got a magnetic flux that's increasing. So that means that I'm getting EMF in my circuit, and I'm going to get a current that is going through there. So the light is going. If I pull this back, again, I got a changing magnetic flux. And now I've got a current going in the opposite direction, and the light bulb goes off. So that's basically it. Everything depends upon what the time rate of change of this flux is. We have two apps. There's one for frequency domain, and there's one for a transient or time domain system. And yeah, they're available on GeoSci. What they basically do is coils. So there's an outer coil here. That's going to be the primary circuit. And there's a current that's going into here, and that's the subscript means primary. And then that's going to give rise to a magnetic field that's impinging upon an inner loop here, a target loop, which is actually characterized by resistance and self-inductance. So let's just think about what's happening in the time domain. So here's our two coil system. If we have a primary field in here, but it's on, and then you switch it off, and then it's 0 after that. The magnetic flux follows the same path, and the time variation of the magnetic flux is 0 everywhere except right here at the turnout, where it's infinite. So that gives you an initial current that's going in here, and throughout that circuit there will be currents that will gradually decay. So the bottom line is I have a current in my primary coil, so that makes a flux through. I turned it off. Now I've got a time varying change of flux that's going to set up a secondary current in that coil. So it's going to have a magnitude I sub s, and then it's going to decay away as e to the minus t upon tau, where tau is a time constant, which is dependent upon the ratio of L upon R. And so if you measured the secondary current as a function of time, you'd see that it's just going to decay away. If we look at the response function, that just tells you how that current is going. So it's e to the minus t upon tau. Depending upon tau, I could get different lines here. And also there's different kinds of ways of plotting. So this is a log linear plot. That's just going to be a straight line. So take the log of that. If I did a linear plot, then we just have this decaying exponential. So both of those kind of represent the same thing, but these kind of quantify what the response function is for a time domain system. So what happens if the signal is harmonic? Right. So now we've got something that looks like this, and there's really nothing that's different in this whole system, except that this primary field never shuts off. It's always on. Okay. So if I looked at this system here, so I've got a primary current, I'd be following this red line here. So that's the primary current. I'd be measuring in here a secondary current, because there is always a time varying flux. And then the question is, well, how could that vary? Well, it has to vary harmonically with the same frequency, because there's just no way it can do anything else. And then with the change, if I look at how things are going to develop in time, it has the same frequency. And the only thing that can vary is its amplitude, and also maybe a phase shift between the primary and this. So this is what the secondary field looks like. So I could take this field here, and this is how many done? So I could take this current here, and I could actually decompose that into two other currents, one of which is in phase with the primary field. So if the primary is like this, then this other one is kind of in phase with it, right? So it's this. And the other is an out of phase component. So if the primary is like this, then this one's kind of going like that. So I could sum these two guys up and get this guy up here. So that's, this in phase and out of phase are just ways of dissecting this green curve to talk about two different things. And mathematically, we could do that just like this, right? So the primary field's like this. The secondary field has got an amplitude. And it's also a cosine omega t, but it could be phase shifted. Then I could break this apart, and I get something that varies as cosine omega t. So this is called the in phase part, or the real part. And I get something that varies as sine omega t. And this is called the out of phase, or the quadrature, or the imaginary. probably the biggest impediment and the biggest source of confusion for all of this when electromagnetic people are talking to geologists or practitioners is these terms here: in phase, real, or out of phase, quadrature, imaginary. We tend to use all of these things simultaneously, and they sound kind of mysterious, but really that's all they are. They're just sort of partitioning this secondary current into these two components. The phase lag has got a formula that looks like this, so it depends upon these three quantities here, which can be combined into something called the induction number. So this is the induction number, and we're going to get the same phase shift just so long as we've got components of these variables all giving the same final number. The response function then for a frequency domain system then kind of looks like this, right? So here was a psi. Here's our phase shift. We can put that back into here, and then we'd have a real component and an imaginary component that looks like this. If you make that into a plot, then we've got this in phase or real part and out of phase or quadrature part that looks like this. So that's induction number, and that's our response. This particular plot is kind of characteristic. If you look in any book on electromagnetics, you're going to see this as the response function for a frequency domain system. And there's some important parts in here. At some level, at low induction level, it's the quadrature part or the imaginary part that's larger than the real. If you get to high induction number, it's the real that dominates. And so they have a role to play in interpretation of the EM responses. So in summary, we could have a step off, we could have something that's harmonic, doesn't matter. They both induce currents via the Maxwell's equations, and those currents generate secondary fields. Let's just take a look at the secondary magnetic fields. So we've got currents, and they generate a magnetic field with a curl in them, and we could go ahead and measure them at a receiver. Our options for doing that is that we could use a magnetometer that will actually measure B. So now we've got a field, so we have three components. So we could measure B. This would be maybe done with something called a flux gate magnetometer. Or we could use coils, which would measure dB dt, because they'd give a voltage when you've got a time-varying flux through them. So each coil would be measuring magnetic fields that are coming in a particular direction. The thing that is extremely important here now is coupling. And we kind of got an idea from our two-coil system. And here's the basic element. Suppose we have a transmitter that's sitting here and it's giving rise to a magnetic field that's coming down like this. Then all of the flux from here is purely vertical. So the total flux that's coming through here is maximized. If we look up here, the magnetic field that's coming from here is running parallel to this coil. So there's no flux through that coil. So this one's called null couple. So this is perfect coupling. That's null coupling. And of course, you can have all kinds of things. So that's the coupling between the transmitter and, let's say, your target. But you could also have another coupling between, because you can take this as being the induced currents in the body, and here's your receiver. All right, so there's kind of two sets of couplings that you could be considering. So that actually allows us to put a lot of things together. Suppose that we've got a system that looks like this. We've got a transmitter, we've got some kind of a conductor, and we've got a receiver. So we could take this system and represent it by three coils. Here's a transmitter loop, Okay, and here's our target loop, and here's the receiver loop. So what we're interested in is, okay, what's that ratio of the secondary field that we measure here? Okay, so that's the field that's coming from here. What's the relationship between that and the primary? Okay, because that's going to tell you something about your strength of your target signal. Just by looking at this diagram, we can basically write down this equation. Because physically we understand what's going on here, right? We've got, let's look at the secondary field. Okay? So we've got to get the energy from here down to this loop here, and the way in which that coupling is going to go is dependent just about geometry. So this is called the coupling coefficient. So if the coupling coefficient is large, then we've got good coupling. If it's small, we don't have very much. And that just completely depends upon the geometry of this loop and that loop. So that's M12. Then there's going to be another coupling between the currents here and the receiver. That's going to be M23. So the signal here for the secondary field is going to be M12, M23, and then there's now the response function of the loop, which is this guy over here. And we want to take a ratio with respect to a primary field, and you can see that just really depends upon M13. So this is kind of nice, right? You just take little bits and pieces that you kind of understand, and the first thing you know, you can take a system like this, and you could actually write out this equation, which now means something to you, but could have been more challenging to figure out what to do. Okay, so that's our quantity that we're really going to be interested in, and this alpha is just this induction number, omega alpha. Okay, so now suppose I've got a system, and I want to figure out what my anomaly is going to be. So I'm going to use a loop system. You can think about it. How many people used, say, an EM31? Anybody? Yeah, so there's a near surface instrument, Geonics EM31. It's got a transmitter here. There's a boom. It's got a receiver over here, and you're just moving this thing across, and then you're trying to see what the response is. So how does all that work? If I'm sitting on this side of Sarah, I've got this. My transmitter is over here. My receiver is over here. My transmitter is going to generate time-varying currents. Those currents are going to give rise to secondary magnetic fields, and I'm going to see them here. And if both my primary field and the secondary field are in the same direction, I get to plot the numbers positive. So if I'm sitting over here, for instance, the farther I go away, then my primary field is falling off over cube, so I don't excite much currents. But as I come closer, I'm going to have more signal that is going to come through. And that is actually going to happen until I reach this particular point where my receiver is directly over Sarah. And then why, so there, at that point I claim I'm going to get a zero. Why is that going to happen? Anybody? Oh, you got archery shot, come on. The currents in this, so I've got a time-varying magnetic field here, okay? In basic plot here. So that's going to give rise to currents that are going to be flowing around like this. And those currents are going to give a magnetic field. The top of it are going to be parallel to the Earth's surface. So there's not going to be any flux coming through this coil. So I'm going to end up with a zero crossing, okay, right here. And then now I'm going to be in this situation. I've got a transmitter on this side, a receiver on this side. Lots of currents that are coming in, lots of flux, right? big signal. It's going to be negative. And then what happens when I come over here and my transmitter is sitting right above that? Yep.
Oh, we have a special geometry of Sarah, there will be no induction.
She's very thin. There is no flux going through her. Absolutely. Right. So that's the point. Now the primary field, there's no coupling with you. You're no couple, and so that's going to give rise to this guy here. And then now when I'm both transmitter receiver on this side, we're back here. So the basic signature of a loop-loop system going over a confined body is going to be one that looks like this. Okay. What happens now? I've got red and black going on here. So my in phase and my out of phase parts, they're actually equal. And the reason for that is that I'm operating, I chose that, with an induction number of unity. So an induction number of unity, the real and imaginary parts are identical. So that means those two curves plot on top of each other. If I change this so that my induction number is less than 1, so now I'm operating on this side, it's much larger than the real, and you can see that's what happens here. So I keep the same shape of the curve because that's geometry, but I change my relative amplitudes because that depends upon the induction response. And then if I go the other way, alpha is equal to 2, now the real part is larger than the imaginary. Okay, so kind of got this idea about how this mutual coupling works, and that you have to kind of look at the flux, and then which way the currents are going, what the magnetic fields are, and how they're coupling with your receiver. What happens if we go for a transient signal? Well, if I put in a time domain system like this, I do exactly the same thing. It's just that so at each point I'm going to turn my system off and continue along. I get the same shape of the curve, but at the earliest times I get the biggest signal. Latest times I get smaller. Dot 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 dot. Okay, no difference, right? Frequency, time, I got the same thing. Okay, so what did we learn? We kind of got a sense about basics of EM induction, response functions, mutual coupling, data for the frequency and time domain systems. We got a circuit model. Like, is that really applicable? Is it applicable to geologic targets? Well, we can see. We can check it out. We can do some numerics. So if we have a simple circuit like this, we can get a response curve that looks like this. Suppose we take this same system, and we're actually going to make it realistic here, right? So we're going to have a transmitter that's sitting 20 meters above the Earth's surface, and we're going to have a receiver that's offset by 8 meters. We've got a background that's very resistive, and we also have a sphere. It's a sphere, 30 meters in radius and 2 Siemens per meter. So the numerical modeling from this using cylindrical symmetry, we'll talk about that in a second, gives you something like this. So you can see that, yeah, qualitatively these things actually look pretty similar. So here's the quadrature phase part, here's the real part, that's the same character. So the point about that is that a circuit model might seem like, wow, that's a bit simplistic. But in fact, you can get a lot of insight sometimes just from a simple model of how things work. The code that developed this is based on a couple of papers, one by Rowan Cockett et al., and then the other one by Lindsay, who's been the prime developer of this guy for EM. And it's built on SimPig, and we're making that's available. It's open source. on here. So that's a 2D cylindrically symmetric, well, it's a code that can handle 2D cylindrically symmetric objects. And you can see how that would have worked for this sphere, right? So we've got a transmitter that's directly above the sphere. So everything is cylindrically symmetric above that, generates the fields everywhere. You can measure those. So this code is available. It's actually forming the heart of some current research that's being done with steel-cased pipes. Because this is all the rage these days in the oil industry. Want to use existing infrastructure to pump current down closer to target bodies at depth, because you need to excite target. And let's go through that. So where are we at this point? Well, we've got some 2-coil apps for frequency and time. Circuit model is a good proxy. We haven't really talked about an important item, and that's the propagation of the energy from the transmitter to the receiver. Well, from the transmitter, actually, to the target, and from the target to the receiver. Because we've been putting everything in kind of in free space. And so the question is, suppose it's got something in there. So in order to do that, we have to start to look at how do the EM fields and fluxes behave in a conductive background. So now I've got to revisit Maxwell's equations. So we've got first-order equations that look like this, along with the constitutive relationship. They can be combined into a single second-order equation that's got both a diffusion and a wave propagation term. Taking for a transfer of that, we get a vector Helmholtz equation now that looks like this. So we got this quantity here. In our quasi-static regime, we actually ended up saying this term is much larger than that and basically getting rid of this. And under that procedure, then K is just the square root of this guy, which can be written out like this. So how does all this stuff fit together? So now we're going to imagine a plane wave coming in. So you can build it. So a plane wave is a wave that's coming in, and the phase is not changing anywhere on a horizontal plane. And one way of thinking about that is you could think about a current sheet. So imagine you've got a big sheet of current up there, and all the current's flowing in one direction. So if I've got current flowing like this, then right-hand rule says that the magnetic field is perpendicular to that. So I've got an electric field in this direction, electric field in this direction, magnetic field perpendicular, and then the whole thing is propagating in. So it propagates in, with e to the minus kz, okay, which, because we've partitioned k, it's got two terms. It's got an exponential here. This is basically a phase propagation into the medium, and this part is attenuation. Attenuation is the big issue here, because we've got to get energy into the ground, and how quickly it attenuates depends upon this alpha coefficient. So if you imagine what's happening, we've got a wave, it's got an amplitude of one surface, and then with depth, it just decays in. There is a point at which the amplitude is decayed to 1 upon e of its value, and that is called the skin depth. Probably one of the most important words and concepts that you can have in electromagnetics for frequency domain is the skin depth. And that tells you the depth at which the field decays to 1 upon e. In the transient signal, there's a couple ways of looking at things. Okay, so let's suppose I make an impulse here, so I have a current, I switch it off. Then at Sarah's location, she initially doesn't see anything, but then as a function of time, the magnetic field is going to rise up, and then later time it's going to decay. So this is what you're going to feel if you're just sitting at one location. The other thing is I could take a snapshot at any particular time. So I turn the field off, and at some time later, I just take a snapshot of the field, and I look at it, and this is what I see. So there is a particular depth at which the magnetic field is a maximum. And that depth is given by this formula here, and it's called the diffusion distance. So it's kind of a representation about where that kind of peak magnetic field is at any particular time. Later times, it progressively goes farther down, deeper. So this is the diffusion distance. That's the concept that is important for time domain EM. And the higher the conductivity, the smaller the diffusion distance. The longer the time, the greater the diffusion distance. We have some apps. Play around. We've got transient and harmonic. And what they allow you to do is to just change the parameters. And you can look at fields. You can look at electric field. You can look at magnetic field. Plot things as complex numbers. Look at an amplitude and phase, or real and imaginary. Lots of ways of looking at these and interacting with just the simple example of a plane wave going into the Earth. There's a lot of insight. Okay, so now we kind of got it, right? We can now start to look at the effects of this background resistivity. We've got to get the energy to the target, so it's going to be some attenuation, and it's got to go from the target to the response, or to our receiver. Let's just take a look, first of all, on the time domain. Actually, it's just kind of interesting to see how much insight comes from the time domain. So we got a buried sphere. It's 2 Siemens per meter. It's basically free space in the background. And then we look at 10 to the minus 5 seconds, which now the new SkyTemp system can actually penetrate. And currents. So here's our sphere, and it's lit up with these currents. So that's pretty interesting. We see the currents are kind of on the outside. Maybe my first question is, like, we don't really see currents in here. But you got a plane wave kind of coming down. Not really a plane wave, it's close enough. Why don't we see stuff in there? Simon? So the currents are just confined to the outside. Why are they not inside?
Because it's different pollution. You have something that's very conductive, then it's going to be a lot less on that object, so it's going to be positive on the surface of the conductive element.
Right, you actually, you said 2 things in there. Both things have relevance. From the point of view of this, since we're only looking at one particular time, okay, then the thing that is of relevance is the diffusion distance. So now we've got an EM field that's kind of propagating in here, but because it hits this higher conductivity, it can only diffuse a certain length at 10 minus 5 seconds. That's basically it. You know, it's almost uniform across here, right? So it doesn't matter where you are on that sphere, the distance in is about the same. So that's a diffusion distance related quantity. If we looked at later time, then things would actually be happening inside, and eventually things would go away, and that would be then an attenuation. Diffusion distance. Okay, so what's going to happen now if I change the conductivity? I'm going to make the background. So it was at 10 to the minus 8. Now I'm going to make it 10 to the minus 2. What do you think is going to happen? So your name is? Yep.
Thomas.
Thomas. Okay. What's going to happen, Thomas?
You might lose some charges up to the surface.
Okay. Anybody else? Oh, come on. Right here? Oh.
I would guess that it would fill up. Yeah, so it's the same. But so that's not.
So what did we just talk about for our getting our energy into the subsurface? Right?
Yes, it's a matter of maintaining the source field geometry, especially. So you would expect that you would have current trying to maintain the source geometry, and if you have a sort of a point source or transmitter here as a dipole source.
Yeah, not really. Anybody else? Think, Lisa?
Maybe say that the energy is decreased.
Right. Okay. So that's more to the point. So we don't really care at this point about point sources and dipoles. It's just we got energy coming in, right? So I got energy coming in. Now I might expect that some of that energy is going to be lost. Okay? Because we just went through that, right? We talked about skin depth and diffusion distance. Okay? So now I'm going to make it more conductive. I make it 10 to the minus 2 Siemens per meter. What happens?
You got a diffusion distance on a diffusion distance. That's it.
Okay, maybe. I mean, we just argued that we should be losing energy.
Yeah.
Looks like that. So what's the deal? Right. Oh yeah. Go ahead.
So the charges will move to the side of the step.
So this is interesting. So now, okay. So I started the morning, DC resistivity, and we talked about charges, right? Then we switched over to EM induction. There ain't no charges. No. Yeah. So this is an entirely different phenomenon, which we will eventually put together early in the afternoon, how we piece these together. But at this point, remember all those currents are kind of going inside. There's nothing crossing a boundary. Yeah? Go ahead.
The current density is consistent.
But we're just, so which sides? So we're going to make this, I mean, the question is, here we're at really resistive, and now we make it conductive, and I don't know, how much has happened? What's going on? Because we had thought that things should decay, right? So if things decay, we shouldn't see so much current. Well, we made it conductive, but remember there's this, you were actually, I think, pretty close with respect to diffusion. It's still, this is more conductive, but at 10 to the minus 5 seconds, the waves have kind of, diffused through. So we don't really see any difference. However, if I now increase that conductivity 10 to the minus 1, now look what happens. Conductor is a conductor, right? So we get time varying magnetic flux. So that's going to give currents up here that look like this. So notice also they're kind of funny, right? Because we got maximum here, maximum there, but that's because the our source current is a loop, right? And so it's got some geometry here, but you can see how there's currents up here. That means we're losing energy. That means that the currents down here are smaller. So now we're starting to get shielded. Just, we're looking for that conductive body, but there's currents up top that are taking away our energy. And if we increase that even more, we don't see the sphere at all. Everything that we're looking for is just happening in that homogeneous curve. Okay, so we put all that together and we do a time domain experiment. We look at a particular time. If it's really resistive, get this. If it's still resistive, but you would get more conductive, doesn't change anything. But then there's a tipping point when at a particular time, then this is what you're seeing. And if it's even more conductive, you're totally screwed. Okay, so that's the effect of induction in the sphere. And that's starting to get now the effect of, okay, I've got a background conductivity. I've got to get that energy down and then back again. So that was time domain. What do we expect is going to happen in the frequency domain? Well, physics is the same. So now let's look at the same configuration, but let's do a harmonic signal. Okay. So now if I look at a high frequency, high frequencies we'll look at more later, but that's kind of like early times. High frequency, I'm looking at here, 10 to the 4th hertz, and that's those are my currents. Now if I make that 10 to the -2, notice again, it's about the same as we had before. I make it 0.1 Siemens per meter. Now you see how I'm shielding, and I increase it to 1 Siemens per meter, and I'm shielding. The same picture, exactly the same phenomenon, frequency, time, and the physics is quite clear, right? You can just see it, right? If I'm not obstructed by anything outside the sphere, I just induce these currents in the sphere, I'm good to go. As soon as that conductivity gets to be to increase, I just lose signal through attenuation. Okay, so what have we learned? Well, we've got circuit model is a good proxy. We need to account for the energy losses, kind of understand the relationship between frequency and time, and there isn't very much. Physics is the same. So let's look at some field examples. So here's some of the case histories. We might not get through all of them today, but we have tomorrow also for people who are interested. But we've already started with this one. That's the DC resistivity. Kind of mentioned this dam monitoring. We can come back to that. Here's one direct from your home ground here, casted, which we have shown. There's only been 2 case histories that we have shown at every place that we've been to. One is Mount Isa, and the other is casted. Other places, depending on the audience, we choose this case history or that case history. But casted is great for mapping paleochannels. Buk Pernong, it's Australia, sort of salinization. Landslides, Austria, is there a frequency domain system. Here's a time domain system, Saudi Arabia for improving a seismic velocity model. I think maybe that's not very much of interest here. For grounded sources, we're going to look at the Indian Deccan traps, see if we can find sediments we need. Here's one that people really loved in certain places, but maybe is not so relevant here. It's using marine EM for de-risking wells for hydrocarbons, and also methane hydrate. This is a big deal coming soon to many countries. In natural sources, we will look at MT, and there's a geothermal system in Iceland. There is one here in Sweden that might be of interest involving landslides and quicklades. Switzerland, there's rock glaciers. This is a GPR. This guy I've got to show you with GPR. It's like the coolest thing ever. It's the use of GPR for self-driving vehicles. Here's another case history from Aarhus, looking at a landfill. So this is IP, and then we're going to finish it up with the IP from Mount Risa. So that's going to be today's case histories. And what I'd like to do now is to go to inductive sources. No. We'll see if this opens. We started off at the beginning of this disk with this thing of inductive sources. And I don't know, it just kept growing. There were more slides coming in, images were high res. And then we got to the point where I couldn't even open on my own computer. But I think this is going to go. If it doesn't, we will go to a PDF. Yeah. There's a zillion slides and lots of case histories. Oh, is it Mike?
No, it's PowerPoint.
Yeah, but it's, so it's that kind of blue line kind of going. I mean, it's only 163 slides, but at the same time, there's a lot of kind of high-res images. Okay, so now we want to go to inductive sources. So what was the motivation? We've kind of already been through that. In particular, this shielding problem is kind of iconic in that regard. So we're going to do a couple of things. We're going to just look a little bit at the basic experiment, although I feel like I should have Espen come up and give a lot of this stuff, but it's okay. You can correct me when I'm wrong. And then we're going to do a time domain EM. And we're going to look at a vertical magnetic dipole, and then we'll do a case history. I think that'll probably take us to lunch. If we can get through that to lunch, then I think the rest of the day is orchestratable. Okay, so here's some important questions. Again, you have to figure out, okay, what's my question, right? So what's the target? Is it surface? Is it depth? It's 1D, 2D, 3D. Where do I put my transmitter? The surface, in the air. What waveform, frequency, time? What's the size of my loop? Remember, there's this moment business, orientation. I got to excite the target, so I need to know the conductivity of the target and the host. Geometry, got all this coupling issues. The receiver, what fields to measure, what instrument. Where to collect the data, how many, how accurate. All these things. And there's no shortcut. There is absolutely no shortcut to doing anything in here. You've got to think critically about each of these guys to kind of maximize what you want to do. So these are all questions of survey design. So the basic experiment we've already seen, right? We've got a transmitter out here that puts out a time-varying magnetic field that generates electric fields everywhere. You've got a conductor, it generates current, and you've got a receiver, measures magnetic fields. Let's just look a little bit at transmitters. So if you've got a large area here, so you've got 100 kilometers, 100 kilometers, or you've got rugged terrain, you really don't have much choice except to have a some kind of airborne system. So here's two. This is a resolved system. That's a frequency domain system. And here's your homegrown SkyChem system. So that's your airborne. If you've got deep targets and you really want to get stuff down there, you might actually need to have a large loop on the surface as your transmitter. What's the big issues here? Basically, whether it's frequency or time, the key factor is moment. Remember, so moment I said was the product of the current times the area. It can also be, if you have multiple turns, times n. So that's how you increase your moment. And your magnetic field is now governed by this. So the moment is important. And that primary field from the loop, especially as you get far away from it, then has that 1 over r cubed decay. That's just geometric decay. And it's got attenuation. So those are the big ticket items. You've got some kind of a transmitter. It's got a moment. It falls off with 1 over r cubed. And it might attenuate. The things you want to be as close as possible to the target. So that means a ground-based system is probably the best. But helicopter would be next, and fixed wing is third. So you're just progressively getting farther and farther away from the target, and you're always worried about coupling. Same slide I showed before, measure magnetic field. So you could have a flux state magnetometer, or you could measure dp/dt with coils. So in the time domain, this is rather nice because the primary field has an off time. So the current is like this. So there's no current in that off time. And the response function then just looks like this. So here's your SkyTem system, with this as being your transmitter, receiver down here. And you could fly that. Here's a ground-based system. This is a helix now. Actually, I'm very, again, really pleased with what we've been able to do at UBC with respect to this. This is kind of interesting. So this is a large loop that's set on the ground. It's a couple of kilometers on side. And then flying over top of that is a total field magnetometer. It's called helix. In the frequency domain, the difficulty is that the primary field is always on. And that primary field is large compared to any secondary field. So that is the challenge with the frequency domain. So you somehow got to contend with that. You have to remove it somehow. So you can either compute it and subtract it. It's a possibility. But the other thing they'll do is have a bucking coil. So here's the transmitter, here's the receiver. So there's a primary flux that's coming through this receiver loop. But if you could make another source, like a little bucking coil that had a total flux through this receiver that was equal and opposite to the primary, kind of good to go. So that's what people do. They generate a system with a bucking coil, so that basically they're just measuring the secondary field. This is how they often do it. So in like a resolve system, you've got a number of loops here for a transmitter, and they're color coded. So this is transmitter, there's a receiver. And notice that they're on the same plane. So we call them horizontal coplanar, sometimes HCP. So those are horizontal coplanar coils. And that's exactly what this is. That's that EM31 I was talking about. So you got a transmitter here. This operates about 10,000 hertz. And receiver here, and you're just moving that thing along that data set.
So what's the one called vertical coil?
So that, so that is a vertical coaxial coil. So it's got this guy. And the reason for him is that it's a coupling issue, right? So if I have a horizontal coil, the magnetic flux is coming in like that. If I have a vertical coil, it's coming in like that. So it offers very different information. So important questions. We're kind of coming back to, okay, so where to collect data, how many, how accurate, depth of investigation. Effectively, it's sort of, what is the footprint of your transmitter? Okay, so let's just take a look at that. Let's go back to the time domain, and if our receiver is a B field receiver, we expect to get something, just a nice decay. If it's BDT, then there's an impulse and a decay. So we're going to be looking at both before and after shutoff. So the footprint of the system, everything always comes back to currents, right? Where's the currents? It's kind of like the mafia guys, right? Like you follow the money and you get them, right? In EM, you follow the currents. And then SkyTem tries to convert that to follow the money. But you could have laughed. No problem. Okay, so the currents depend upon your transmitter, your waveform, frequency time, or the background conductivity. So what we're going to do is we're just going to look at a simple example. Let's say a vertical magnetic dipole and over a homogeneous Earth, and just see what we get. So here's the setup. We're going to have an Earth that has got a 100 ohm meter background. We're going to have a vertical magnetic dipole that's sitting 20 meters above the surface. And we've got a receiver here at that red dot. So questions about the currents: where are they? How strong? How do they depend upon the conductivity? And what are the resultant magnetic fields? So we're going to have, so this is all in an app that's available to you. There's a cube here in which we can look at sort of what's happening in plan view and also what's happening in cross section. So that's what we're going to do. So we're going to do a time domain, like a step off, okay? And then we're going to look at a time of 0.01 milliseconds. The current density, so we got a loop that looks like this, so our transmitter is a circular loop, right? And that means that the currents in the Earth are going to follow that same pattern. So the currents in the Earth on plan view now look circular. And if we look at depth, okay, the currents are going to be coming out on one side and going in on the other. So in a cross section, the currents are kind of going in here, out here. In plan view, looks like that. Right, so they kind of follow the transmitter. And then now you could ask, okay, well, what would you expect for a magnetic field from that? So those are my currents. What do the fields look like? Well, you've already got an idea, right? Because exactly, so each current filament, so you can imagine these, like for every point I take out here, there's another one coming in here. There's that. So everything is circularly symmetric. So there's just like a zillion little filaments, circular filaments, each of them going to give rise to kind of like a magnetic dipole field. And then when I look at that magnetic field, basically, magnetic field lines are going to be concentrated right in here, right? Because that's where, here's the locus of the high currents. So I'm going to expect the strongest magnetic fields are going to be pointing vertically. And that's exactly what happens. So the strongest magnetic fields are here, but we still got magnetic fields that are coming up here. And here's our receiver. Up here, you can see, there's my fields. What happens when we watch things through time? Well, if I look at something that's really early, which is basically 2 microseconds, I got this diffusion distance term. That's 18 meters. If I actually look at the currents in the Earth, so 18 meters is kind of in about there, so you can kind of see where the currents are. If I look later, got a diffusion distance of 38 meters, and then later, sort of 75 meters, and then later 132. Right? So as a function of time, what's happening? I initially start off with currents that are just sitting kind of right underneath the transmitter. And then as a function of time, they kind of go. And that's quantified a little bit. There's a really famous paper by Misak Navigyan, 1979, who kind of talked about the representation of these currents as being smoke rings. So I kind of have have a filament current that is going down into the earth and kind of sort of meandering down and outward, on kind of an angle of 30 degrees. And that's kind of a nice way to think about it. So we've got currents that are initially induced. As a bunch of time, they just kind of go down and up. So some important points here is that the currents flow in the same direction as the transmitted currents. They diffuse outward, downward. Each transmitter has got its own footprint. And the maximum resolution, this is actually really important, especially after having talked to Esben just a couple of minutes ago, is that the maximum resolution occurs at the earliest time. So you want to have early times so that your currents are just like as close as possible and to the surface of the earth and as confined as possible. That gives you your maximum resolution and allows you to capture that near surface variation. On the other hand, the latest times are going to be reflective of where the currents are at the end. So that's going to tell you something about your overall depth of investigation. Okay, so those are like big ticket important point. The earliest time and that diffusion distance kind of tells you, what you might be able to see, how close to the Earth's surface, and what that high scale resolution is. And the latest times give you some idea about how far you're actually seeing. And clearly, you're not going to have. You were asking me about resolution and stuff like that. So it's at early times you've got maybe stuff up here. At late times, I mean, you're seeing deeper, but everything is diffused. I mean, you are not going to have really super resolution, even though you might be able to see something today. Okay, good. So now we kind of got that. How about a layered Earth? Let's make it just a little bit more interesting. So we're going to take the same structure, except they're going to put in a layer here, 20 meters thick, and make it different resistivities. Okay? So we can make it highly resistive. So the background is 100. So we can make it 1,000 millimeters, 10, or 1. And then the question is, what's going to happen? So first of all, let's look at our canonical case. So here's 100 ohm meters. Looks like that. Now suppose I take a layer in here, okay, and I'm going to make it resistive. Okay, what do you think is going to happen to that picture with the currents? Are you raising your arm to it?
Sure. So you're going to have less current running in that particular layer, but it shouldn't really be shielding or anything. So it's like pretty much unchanged.
So does that qualify for the gold star? It's getting pretty close. Yeah. So there's a couple of things. So what if we put in a resistive layer here? It's exactly as Tui said. There's no currents that are built up. There is an electric field. You don't get around that. There's a big electric field, but remember the current is the product of sigma and the electric field. So there's not very much for currents. The other thing that's really interesting is that you actually enhance your depth of investigation a little bit. You're actually seeing a little bit better here than here. It's not quite so obvious on there, but why would that be? What? Yeah, why?
Yeah, because that energy that's actually absorbed over that portion that is 100 meters is not being absorbed on the right hand side. So it kind of you could imagine that the current actually jumps over that part and being being distributed in the deeper part instead.
Perfect, perfect. So the point is here, it was resistive, so there's no energy losses that are going through. So it's now impinging on here, and yeah, it can actually create more current. So the concept of having a little bit more of a resistive layer in here can actually help. Okay, that's the resistive layer. What happens if we put a conductive layer? So now we're going to make it a bit more conductive.
Yes, and the current was running conductively, and you don't see that much better.
Yeah, so the current is going to be primarily concentrated in that conductor. The color scales aren't the same; they're still more current. But this is now the primarily where the currents are is in that conductive layer. And if I increase that even more, then you know exactly what's going to happen. The current's going to be almost all in that conductive layer, and also it's not even going to get through because now it's attenuated. So just those simple things, you start to build up an appreciation for how things are going to behave in that. And when you look at the magnetic fields, yeah, you see they all vary, but everybody's got some kind of signature here. What's interesting with respect to quantifying how important something is actually the sounding curve. So there's probably two things that you guys should invest in. I would invest in SkyTemp, and I'd invest in Hall's chocolates. Okay, so here we have a uniform Earth, 100 ohm meters, and now I'm going to do my sounding curve. So this is going to be time, and here's my dB/dt, here's my signal, and it looks like that. If I put in a resistive layer in here, then I get the dashed lines. So now my sounding that I obtain it's just really not very much different. So I hardly can see this resistive layer. But if I put in a conductive layer, a low resistivity layer, now you can see how much has changed. So what you are provided with are these sounding curves. And here's one where you have this resistive or a low resistivity layer, and here's one where you've got something that is really conductive. It's 1 ohm meter. So that's huge, right? It's almost 1.5 orders of magnitude. Let's take a look at now an airborne survey that's going to try to find a conductive sphere. Okay, so we got a background, 10 to the minus 2 Siemens per meter. This is 1 Siemens per meter. Here's our sphere. And we're going to fly our survey across here, so each of the dots will get a sounding. And then we could plot the values up at different time channels. So this is going to be a data map at a particular time channel. And then across this line here, we can plot a profile of what the data would be like at any particular time. So initially, at very early times, 0.025 milliseconds, then we're just operating up here. We're really seeing this half space. A little bit later, our map looks like that. Profile looks like that. So we're starting to see something. The sweet spot is down here at about 0.3 milliseconds. So now we've got a well-localized body here, and a cross-section looks like this. And then a bit later, so now it's starting to die out. And then a little bit later. That's what your survey would look like. And there's your data. If you kind of put it all together, your plan maps would look something like that, with the sweet spot for finding that particular sphere in that background is about 0.3 milliseconds. And your time decay profile plots look like this. So at your highest signal is at the earliest time, but you're not seeing anything other than just that half space. And then at progressively later times, your curves kind of come like that. So, and here's your sound. Okay. So some systems that are out there. First of all, there was the SkyChem. This was 2006. It's a long time ago. It has both a high moment and a low moment system. So here's your transmitter coil, and the high moment is something that puts in, higher current. Well, you have a higher moment, but the problem with having a really high current and trying to switch it off is that it's very difficult to switch things off quickly. So you do the best you can, but the earliest time channel that they had for this one was 47 microseconds. So then they have a low moment system that allows you, so the waveform for a high moment system looked like this, the waveform for the low moment system looks like this, and you're able to shut it off more quickly, and that allowed to get back to about 12 microseconds. So really you want to get back as close as you possibly can to 0 here, because that's going to give you your highest resolution and find the near surface things. And yeah, then you're going to measure at a whole bunch of time channels that are logarithmic space. So that's the that's the two things. I forgot to mention that the peak current in here was 90 amps. Remember, so the moment depends upon the product of the current, the area, and the number of turns. So the area is going to be fixed, but you can change the current and you can change the number of turns. So that gives you this. And for here, for the low moment system, 40 amps, 1 turn, and you're able to turn that up quickly. The VTEM, many similar aspects. The transmitter loop is around the outside, and you're measuring magnetic fields on the inside here. The waveform is a bit different, but you have the off channels. So, these systems all kind of vary a little bit with respect to which waveform, how fast, how early can you get information, what time channels and things like that. From the point of view of what we're doing here today, they're all pretty similar. As far as you put a waveform in, turn it off, you measure it. Sorry, Esma. Sorry, that was a real blunder on my part. Let me say, from the point of view of all the systems that are out there, they're all the same except for SkyChem, which is just clearly so above and beyond anything else that's there. It almost like we should probably have an extra slide. We'll do that. Okay, so let's do one case history, and I think we can probably break for lunch. So I'm going to do a case history, your case history, on groundwater. So it's casted, and I hope I don't tell any lies here with this. There we go. So here's the here's the area in Denmark, up in here, and here is the survey area that is going to be done. And really, the basic problem, or the thing that is people want to understand, is that there's a background here at depth of Miocene clays, and there's a lot of paleo channels that are in here. They're basically sands and gravels and bits of clay. But here's where your groundwater is. So you want to distinguish what these guys are, and maybe even get some information about what is going on inside these paleo channels. Actually, the thing that I really like about this case history is that I think it puts geophysics into a proper context of how it should be. Because if you're looking at something like this, you've got a complex region, then really you don't care about what the electrical conductivity is. You really care about what the geologic structure is, and ultimately you want to make a hydrogeologic model that could be used for predictions. And the thing about this area is that one of the questions to be addressed is like, okay, so suppose I put a well in here and I start drawing water out. Okay, I'm getting water. Where's the water coming from? It's pulling out here. It's coming from over here, here. What's happening? Okay. And the other thing is like, okay, suppose I put two wells. I'm going to draw water out of both of them. Then, are they kind of connected at depth? Are they independent? I mean, what the heck is really going on? And that, I think, is why this particular case history so resonates with me, because that is kind of very often the role that geophysics can and should be addressed, to kind of help solve a much larger kind of problem. So first of all, we look at properties, and there's a number of different units here, but the big one is these sediments, or these clays underneath, which are have very low resistivities. So it could be anywhere from maybe 1 to 10 ohm meters in here. So that's a very conductive environment. And then the rest of the material that's here, these paleo channels, they can be combination of silts and sands, and have some clays in them, but they're kind of intermediate. So as a first order, you're really trying to find these very low resistivity paleogene clays. So our survey is the SkyTem system. So here's our transmitter, here's a receiver. It's mounted there, so it's kind of null coupled with that primary field. High moment, low moment configurations, 300 square meters for an area. And the data area is given by here. So the blue lines indicate where data were acquired. 300 odd line kilometers of data, 100 meter line spacing. There's a lot of cultural noise, so have to remove some points, but that still leaves you with quite a few. So the processing and inversion all done with the Aarhus workbench. You do have a 3D environment, but you can go a long ways by just using what are called quasi 3D inversions, kind of laterally constrained. So basically, you're doing a 1D inversion, but it's kind of connecting to its neighbors so that nothing is going crazy. So you end up with perhaps hopefully just a slightly smooth version of a full 3D, and perhaps get out just as much information. So I think it was 9,500 soundings, and 25 layers was in. So that means that you've done a whole host of these, basically 1D laterally constrained inversions, and now you've got a cube. So now you can take that cube and you can slice it at a particular depth. So this was 5 meters above sea level, and you can see by looking at this that there's regions in here that are really high resistivity. So 5 meters above sea level. There's patterns here of red, which are resistive, and blue, which are very conductive. The quantity that was really of very much interest is, what is the depth to the top of this paleogene clay? Right? So you have these kind of root-like paleo channels coming out. What's the depth of them? And here's the mean altitude above sea level, and you see that there's really strong blues in here, which means that these guys are really incised, and here's sort of shallow. So you can see that there's structures that are coming in. So those were analyzed, and used to kind of delineate, 20 odd buried valleys that are kind of cross-cutting structures. So that kind of gives you, a geologic model. And then now from that, and here's actually one part that maybe before we go, I can kind of get clarified, because there wasn't a lot of information in the paper, but now to then use the borehole information as well as the resistivity inversions and actually come up with a hydrogeologic model. So there's a little bit of a step that goes in here, but basically we've got the EM kind of giving rise to what the valleys are, but they also have a gradation in electrical resistivity as you go through those, and you've got some boreholes, and you can mix and match with respect to using the EM as a proxy and generate a full hydrogeologic 3D model. Once you got that, you can put that into ModFlow, and then now you can start to answer the question that we talked about before. So suppose that you have a well here, you're going to pull water out, and now you're asking the question, well, where is it coming from? Well, you can see you're pulling it out here. It's not coming from here. It's not coming from here. It's sort of coming from here along that channel. Similarly, if you do the same thing here, it's kind of coming from around here, and arguably there's almost getting to be some connectedness there. So that is a really, really useful piece of information, and this gives you now a model from which, a groundwater hydrologist can start to make some, you'll get some information about, okay, if I inject here, or if I pull out here, where's the water coming from? How is one thing connected with the other? And really answer some, kind of important groundwater hydrology questions. So I said that's why I really like this particular example. Is it not only shows like, okay, I managed to get the 3D conductivity structure, but going this extra step and combining it up, I think really shows where the value added comes from for geophysics. Okay, so this one is definitely not of interest, and it's also 12:30. So does anybody have any questions?
Might actually be of interest for like a quick.
Oh yeah, okay. That's a good point. Okay, let me just flip through. So this was an airborne time domain EM experiment. It was provided by Danielo Colombo, and it's in Saudi Arabia, and it's a place called Wadi Saba. And the general idea, and I'm going to flip through this really quickly, is that there's a region here, and there's all kinds of complicated structure underneath that really screw up the seismology. You just can't get proper static shifts, so you get different kinds of features underneath, karsting and wadis and stuff, and they just kind of screw up the seismic analysis. So the essence, so there's a time domain experiment here, and here's I think an impressive picture. So what you're looking at here, so it's a time domain EM at a particular depth. Okay, they're doing so inverting the plotting. Actually, this was a plot of the apparent resistivity in ohm meters, and here's a time slice from a seismic cube. So you can see here that there is a very, very large correlation between the apparent resistivities and the seismic cube. Images are the same. So what that allows you to do, with a little bit of extra analysis, is that it says, wait a minute, I don't know how conductivity and seismic velocity are related exactly, but I do get the idea that the shapes of structures are going to be the same. So I could do a kind of a cooperative inversion so that I do the EM inversion, and then use that as some kind of constraint in the seismic tomography and kind of put things together. And that's basically what he did. Again, it was the same 1D inversion for each sounding, lateral constraints, and you could kind of put things together formally or not, but basically it's allowing going to invert both of these data sets cooperatively or jointly. And I'm going to do it in such a way that when one of them changes, I'm going to ask for the other one to change too. And where one of them's not changing, I'm going to ask for the other one to be not changing. So that's a level of information. It's going to structure inversion with a structural information. And yeah, so here's a case of looking at the P wave velocity with from the seismic tomography without EM, and here is with the EM. So you've just really cleaned things up, and yeah, the result of that was yeah, a system like this where you eventually use this, got a better velocity model for doing your seismic static corrections, and going ahead and inverting them and getting a much better seismic section. So it was really I think a real big step forward in actually how to combine these guys. Okay, so that's where we'll leave this. Then we're going to pick it up this afternoon. We're going to do frequency domain EM, but we've already got through the physics. And then we're going to do something that's really interesting. You'll like this because it's not part of your background, it seems like. And that is actually to look at a grounded source. So in a grounded source, we're going to do kind of like a DC, right? Put two probes in the ground. But then we're also going to run a time-varying current through that. So now what happens? There's all kinds of really interesting phenomena that happen. And yeah, we'll explore that after lunch. Okay, good.
So lunch is just outside. It's just sandwiches. So you just grab one. There will be two kinds only. So it's either chicken